Hello students, let us discuss ionization enthalpy in the chapter Classification of Elements and Periodicity in Properties. As we have already discussed, in an atom, electrons are attracted by the positively charged nucleus. So, the process of removal of electron, that is an outermost electron from an atom, is called as ionization. The process of removing an electron from an isolated atom to form a positive charge, this process is called as ionization. So, in order to remove an electron from an atom, energy has to be supplied. This energy is called as ionization energy. It is defined as ionization energy is the amount of energy that an isolated gaseous atom requires to lose an electron in its ground state. So, the energy which is represented here, that is ionization energy, its unit are kilojoule mole inverse. So, instead of using the word energy here, we'll use a new thermodynamic term, that is enthalpy. So, we come up with a new word, ionization enthalpy. What is enthalpy? It relates to energy. That is a thermodynamic concept which we are going to discuss in the chapter thermodynamics. So, the unit of ionization enthalpy, which I am writing in short IE, that is kilojoule. Why? Because it is a form of energy. Therefore, kilojoule per mole. Let us discuss what is this ionization enthalpy in detail. Ionization enthalpy, that is nothing but the energy required to remove an electron from an atom to form ion. So, let us discuss it with an example. Sodium atom. In the case of sodium atom, there are 11 number of electron, that is 2 electron in the first shell, 8 electron in the second shell. So, there is a single electron in the outermost shell which is marked as red color here. Now, it will lose this electron and form sodium ion. Now, when you look at the electronic configuration, that is 2, 8, because this single electron is lost by the atom to form the ion. So, here one electron is lost, that is represented like this. Sodium atom give rise to sodium ion plus electron. Now, always the electron numbers get balanced here. You can check here 2, 8 plus 1, that is 2 plus 8 plus 1 equal to 11, 2 plus 8 10 and plus 1 electron, that is 11. So, we can say that the sodium atom, it loses 1 electron to form sodium ion. So, in order to lose this electron, certain amount of energy is required. That energy is called as nothing but ionization enthalpy. Let us take another example. Magnesium. Magnesium, the electronic configuration is 282. That means 2 electrons are there in first shell, 8 electron in the second shell and 2 electron in the outermost shell, which is marked here red color, electron which is marked here. So, in order to stabilize, that is in order to complete the octet, it will loses the outermost 2 electron, which is loosely attracted electrons. So, it loses these 2 electron and form the magnesium ion. First, it loses a single electron, then it become like this, that is Mg plus. With the loss of electron, 1 electron is lost, so it become Mg plus. Now you can see the configuration 281. So, amount of energy which is required to lose the single electron, that is represented by ionization enthalpy, that is first ionization enthalpy. That means the energy required to remove the first electron, that is first ionization enthalpy. But still it is not stable. So in order to get stabilized, one more electron it will lose it. And then it form Mg2 plus ion. Now you can see the configuration 2, 8. So here the second electron is lost. So the amount of energy is required to lose the second electron is represented by IE2, that is second ionization enthalpy. So from this we come up with the new terms here, that is first ionization enthalpy and second ionization enthalpy. That is the energy required to lose the first electron to form Mg plus charge, that is first ionization enthalpy, and the energy required to lose the second electron to form Mg2 plus ion, that is called as second ionization enthalpy. So let us define these. First ionization enthalpy is the energy required to remove the first electron, that is X give rise to X plus plus electron, and the second ionization enthalpy is the energy required to remove the second electron, that is X plus. Already there is one plus charge, one more electron is lost to form X2 plus. Similarly, the third ionization energy can be defined as the removal of third electron. The energy is required, that is third ionization enthalpy. Therefore, Mg2 plus, from this one more electron is lost to form X3 plus. So we can say that depending upon the number of electron is lost, there will be first ionization enthalpy, second, third, and so on. So these are the definition. So in simple, what we can say, the ionization enthalpy is the energy required to remove an electron from an atom in its gaseous state. When we compare the ionization enthalpy, that is first, second and third ionization enthalpy, it is observed that the ionization enthalpy, that is the first ionization enthalpy, when it is compared with the second, it is observed that second ionization enthalpy is greater in compared to the first ionization enthalpy, and the third ionization enthalpy is greater in compared to the second. Because in the case of first ionization enthalpy, the electron is lost, that is electron is removed from the neutral atom. That will be little bit easier work, but if the electron has to remove from a positively charged ion, that will be quite difficult. And if there are two positive charged ions, that is little bit more difficult. So we can say that greater the ionization enthalpy, that means greater energy is required to remove the electron. So since it is easy to remove the electron from a neutral atom then in compared to the removal of electron from a positively charged ion. So we can say that the first ionization enthalpy is minimum, then it is second, then third is greater than the second. So from this we can say that the third ionization enthalpy is greater than second, then first. So we can say that depending upon the charge, we can say that the first ionization enthalpy is minimum, then second, then third. And ionization enthalpy is always positive. It means that always the energy is required to remove the electron from an atom to form ion. Therefore, ionization enthalpy is always positive. So these are the two important reasoning questions which always comes in the exam, that why the ionization enthalpy is always positive and why the second ionization enthalpy is greater than the first. Now let us discuss the factors governing the ionization enthalpy, which are size of the atom, nuclear charge, screening effect, penetration effect, electronic arrangement. So we need to discuss these points in detail. So first of all, let us discuss about the size of the atom. Let us compare the size of lithium atom with the sodium atom. Definitely the size of sodium atom is greater in compared to lithium, as here the outermost electron is its quite distance from the nucleus. So we can say that with the increase in the size of the atom, there is decrease in the attractive force. Here the electron, single electron, is more attracted by the nucleus because the distance between the nucleus and electron is lesser. But here the distance between the outermost electron and the nucleus is larger. Therefore, this electron will experience less effective nuclear charge. That means it is less tightly held by the nucleus. As a result, it is easier to remove the electron when it is quite at distance from the nucleus. So we can say that with a increase in the size of the atom, we can say that less energy is required to remove the electron. That means the ionization enthalpy decreases with the increase in the atomic size. Charge on the nucleus. As we know that the nucleus have a positive charge. So when there is 11 number of electron in an atom, there is 11 number of positive charge in the nucleus. So since the electrons are attracted towards the nucleus, so greater the nuclear charge, it is not easier to remove the electron. So we can say that with the increase in the nuclear charge, it becomes more difficult to remove an electron. Thus, ionization enthalpy increases. That means greater the nuclear charge, greater will be the ionization enthalpy. Now let us talk about the next point, that is penetration effect of electron. In the case of multi-electron atoms, the electrons in the S have a maximum probability being found nearer to the nucleus, and this probability goes on decreasing in the case of P, D and F. In other words, we can say that the S electron are more penetrating towards the nucleus than the P, and the penetration power decreases in this order. Since the probability of finding of S orbital is closer to the nucleus, that means the S electrons are difficult to remove. So we can say that the order of force of attraction exerted by the nucleus on the various subshells are in this order, that is S is greater than P, then D and F. Since S are found closer to the nucleus, therefore these electrons are difficult to remove. So the S electrons will experience greater force of attraction by the nucleus than the P, then the D and then the F. Thus, it is easier to remove the electron of F, then D, then P, then S. That means the removal of S electron is most difficult one. This is called as penetration effect. So we can say that for the same shell, the ionization enthalpy would be more to remove S electron than the P, which is more than that of D and F electrons. Next factor governing the ionization enthalpy is shielding effect, which is also called as screening effect. In atoms, the electrons we can categorize into two types. The electron which is present in the outermost shell, that is called as valence electron, which is represented in yellow color here, and the electron which is inner to the valence shell is called as inner core electron, which is represented by red color ring in this. And there is a nucleus at the center. Shield means a protective layer. So in this you can see that the valence electron is shielded, or we can say protected from the nucleus by the inner core electron. That means the inner core electrons this layer will form a protective layer that protect the valence electron from the effect of the nucleus. We can say that in a multi-electron atoms, the outermost electrons are shielded or screened from the nucleus by the inner core electrons. This effect is called as shielding or screening effect. As we know that electrons are attracted by the nucleus. We can see that each electrons are attracted by the nucleus, and there is an electron-electron repulsion also. Since the inner core electrons are closer to the nucleus, they will experience a greater force of attraction in compared to the outermost electron because they are at a distance. So here the inner core electrons, these experiences a greater force of attraction in compared to the outermost shell electrons. So we can say that the outermost electrons are protected, shielded or screened from the nucleus by the inner core electrons. This effect is called as shielding effect. So the inner core electrons can be called as shielding electrons, and the valence electrons are shielded by the inner electrons. So the shielding effect is the reduction of attractive force between the nucleus and its outer electrons due to the blocking effect of inner electrons. So because of this, we can say that the outermost electron will experience a very less force of attraction. So the outermost electron can be removed easily. That means the ionization enthalpy decreases. So we can say that the more electrons shielding the outer electron shell from the nucleus, the less energy required to expel an electron from the atom. It is because of the shielding effect that the ionization energy decreases from top to bottom within a group. So, in short, we can say that greater the shielding effect, lesser will be the ionization enthalpy. Next factor, that is electronic arrangement. When we talk about the electronic arrangement for the second period element, the elements are lithium, barium, boron, carbon, nitrogen, oxygen, fluorine, neon. When we write down the electronic configuration in the orbital form, it will be in this way. In this, it is clear that the element like beryllium, in which they have fully filled orbital, and the element like nitrogen, in which they have half filled orbital. Why? Because 1s2 that is fully filled, 2s2 that is also fully filled, 2p3 is half filled orbital. So we can say that fully filled and half filled orbitals are more stable orbitals. We can say that they have stable configuration. So in such a case, if the atom have a stable configuration, they will not lose the electron easily. So they will be having high ionization enthalpy. So when we compare the ionization enthalpy for these elements, it will be in this way. As we know that from left to right in a periodic table, the size is decreasing. We know that the size is decreasing, as we have already discussed. The size and the ionization enthalpy have an inverse relation. Therefore, we can say that ionization enthalpy is increasing. So it will be in this order. But in this you can see the variation here. This is because half-filled and fully filled orbitals are more stable. So this variation because beryllium have a more stable configuration and nitrogen also have more stable configuration with respect to the other element. So they will have a experiences a little bit greater ionization enthalpy. So the order will be in this way. And from this we know that the noble gases have a high ionization enthalpy because they have more stable configuration. In the noble gases, when you look at this, the outermost electrons are fully filled. We can say that they have more stable configuration. As the octet is complete, therefore we can say that they are the stable element. That's why they does not react easily with other elements. Because of the high stability, they will not loses the electron easily. So in order to remove the electron from its shell, high amount of energy should be given. That means they have extremely high ionization enthalpy. Same thing when we talk about the third period element. When we arrange these elements in the increasing order of the ionization enthalpy, for that we need the electronic configuration. When we write the electronic configuration, in this it is clear that the case of magnesium, in which they have fully filled orbital, that is 3s2, and in the case of phosphorus they have half filled orbitals, that is 3p3, 3s2, 3p3. So we can say that they have more stable configuration. Fully filled and half filled orbitals are having more stable configuration. Therefore, they experiences a greater ionization enthalpy. That means high energy is required to remove the electron from these element. So the order of ionization enthalpy for the third period element will be in this way. So here you can see that magnesium have high ionization enthalpy. Here phosphorus have high ionization enthalpy. So the ionization enthalpy is in this order. From this we can conclude that half-filled and fully filled orbitals are more stable. Therefore, greater ionization enthalpy is required. That means high amount of energy is required to remove electron from a stable configuration element. Example, noble gases have most stable configuration. Therefore, they have high ionization enthalpy. The elements like beryllium and magnesium, which have fully filled orbitals, therefore high ionization enthalpy. And the elements like nitrogen and phosphorus have half-filled configuration, therefore they have high ionization enthalpy. From this plot, it is clear that the ionization enthalpy is increasing with the increase in the atomic number that is left to right in the periodic table. That's why the plot is moving upwards. But here you can see some variation, that is beryllium, because of a stable configuration, they have little bit higher ionization enthalpy. Similarly, nitrogen also have little bit higher ionization enthalpy. Therefore, this variation is clear in this plot. Similarly, the plot between lithium, sodium, potassium, rubidium, cesium, that means it is a plot which showing the ionization enthalpy of the element in a group, that means top to bottom. As we have discussed, top to bottom the size is increasing, therefore the ionization enthalpy is decreasing. Therefore this plot is moving downward. And here also you can see some variations. So these are the two plots which explain the ionization enthalpy of the elements. Ionization enthalpy is represented as delta H and here I. This is a representation of ionization enthalpy, and the unit of ionization enthalpy is kilojoule per mole. This explanation, this type of representation, because it is an enthalpy, that we'll be going to discuss in the chapter thermodynamics. So ionization enthalpy is represented in this way. There is also one more plot which is given in your textbook, that is a variation of first ionization enthalpy with atomic number for element 1 to 60. So these are the plot which shows the ionization enthalpy of element from 1 to 60 atomic number. After the discussion on the each point, that is each factors, that is size of an atom, nuclear charge, screening effect, penetration effect and electronic arrangement, we can conclude that when the size of atom increases, ionization enthalpy decreases. Therefore, we can say that ionization enthalpy have inverse relation with the size. When the nuclear charge increases, ionization enthalpy also increases. So we can say that it have a direct relation with ionization enthalpy. Screening effect, when it is increases, ionization enthalpy decreases. Therefore, it have an inverse relation with ionization enthalpy. And penetration effect, the electron in the S experiences greater attractive force to the nucleus. Therefore, the ionization enthalpy is in this order, that is S greater than P, which is greater than D and F. So, and depending upon the electronic arrangement, we have discussed that the atoms which have a stable configuration, that is half filled and full filled configuration, in order it is already stable, therefore it will not have a tendency to lose the electron. Therefore, high energy is required to remove the electron. Just like we have discussed the case of noble gas atoms. So, they have high ionization enthalpy for the stable configuration. So, in short, we can learn in this way, that is, size of the atom have inverse relation with ionization enthalpy. It have an inverse direct relation with the nuclear charge, inverse relation with the ionization enthalpy, screening effect, penetration effect in this order, and electronic arrangement, high ionization enthalpy for the stable configuration. As in the periodic table, when we move from left to right in a period, we can find out that the size is reducing, therefore ionization enthalpy is increasing. But there is an exception cases also in between that we have discussed. And when we move from top to bottom in a group, as the size is increasing, therefore we can say that ionization enthalpy is decreasing. So from a periodic table, we can say that the ionization enthalpy increases from left to right and ionization enthalpy decreases from top to bottom in a group. So this is all about the ionization enthalpy which we have discussed. We discussed about its factors and how it variate in the periodic table. So this is all about the ionization enthalpy. Have a nice day.